Progress report video for Will Andersen from MIMS 5001 Optimization. In my previous video, I discussed how my project was based on the FDA Round Robin Challenge, in which researchers, given the following geometry, were asked to simulate blood flow through it using ANSYS software to find good models to represent this. My project aims to correlate parameters in the model's layout to shear forces. Blood, being a shear-sensitive material, can be damaged by strong shear forces, and so it's desirable to know what the strong shear forces are in an operating medical device so as to avoid damaging blood that runs through it. The original goal of the project was to correlate the parameter L to shear forces in the latter regions of the pipe. However, on experimentation, it was found that the ANSYS model, shown below, did not readily respond to changes in the design layout of the geometry. In other words, changing the geometry of the model caused it to not function. As a response, I chose to focus on a different parameter. In other words, as an engineer, rather than using optimization to optimize the design or the layout of the apparatus, I instead chose to use optimization to optimize the performing operations, the performing conditions of the apparatus. Rather than focusing on how to design the device, focusing on how to run materials through it such that they don't undergo damage during operation. So, what I chose to do was refocus the scale of the project to the mass flow rate, m dot, and how it correlates to the shear forces. In other words, as mass flows in through this side at varying rates, how does that affect shear forces throughout the entire apparatus? To this end, I gathered data at 10 different points, 10 different m dot rates. I gathered data that came in this region here as it exits the throat, and I gathered data for just outside the sudden expansion here. And in both those cases, we took profiles of the radial location versus the shear forces experienced. And then additionally, I took data for the wall shear along the pipe wall. The results looked something like this, and these are examples each from one particular m dot value. Now, if you plot the maximum shear force on any one of those given profiles and plot it out for each m dot flow rate, what you get are plots that look like this. And I'd like to point out that there's a plot for the max shear force in the positive direction, and in the case of backflow, there's also one for the max shear force in the opposite direction, though it is much smaller. Essentially, what you get is here you have a linearly decreasing profile. As m dot increases, shear force linearly increases with it. But here you have something a little more exponential looking. Additionally, if you plot the wall shear, and this is going back to looking at just one trial, just one m dot, whereas the previous plot was a compilation of many m dots and their maximum values. If you look at one profile and its wall shear, you get a shape something about like this. And so ultimately what we've got is we've got a fair number of options here for what to analyze for our optimization analysis. And what I'm thinking essentially is to create, so if we went with this data, it's perhaps a little too simplistic, versus if we can create some sort of a response surface where the two parameters are m dot and x location, essentially compiling the 10 different plots of this for the wall shear for each different m dot rate. We could then use some sort of optimization software to effectively predict with less computational difficulty what the problem areas will be based on experimental data what the problem areas will be for high shear forces in a medical device's layout, and use that as a low computational power method of designing for performance.